Hi everyone, got a bunch of top tips and reminders for the upcoming A-Level Chemistry Paper 2. So I've already done one for Paper 1. If you haven't seen that, I'll put the link to that at the top of the screen now. So just like the Paper 1 video, I've just put together a bunch of reminders for the kind of topics tested on Paper 2. And a lot of what I'm going to say is based on common mistakes that I see unfortunately in student answers. But don't panic, they're really easy to put right. So the main reason why I make these videos is because of messages like this. So if it worked for this person, there's no reason why it can't work for you. The first few slides I'm going to look at is just general stuff, and then we'll get into the specific organic topics. Okay, so starting with classification of organic compounds. So a hydrocarbon contains carbon and hydrogen only. Saturated compounds contain carbon-carbon single bonds only. Unsaturated compounds contain multiple carbon-carbon bonds, so double, triple, and also aromatic rings, so benzene rings. Aliphatic can be straight chains, branched chains, or non-aromatic rings, and those rings can be branched or unbranched. Aromatic compounds must contain one or more benzene ring. Alicyclic is a ring, but it can't be an aromatic ring, otherwise it would be an aromatic compound. Cyclic compounds just contain any kind of ring. And finally, an alkyl group is a group that has the formula CnH2n plus 1. So there's 3 examples for you there. Moving on to connectivity, you wouldn't believe how many mistakes students make for this. So what we're talking about here is making sure that your atoms are connected to the right ones. So I'm going to show you a couple of examples. So you can see the alcohol on the left has been drawn correctly because the oxygen is bonded to the carbon, but you can see on this one it's not bonded correctly because the hydrogen isn't bonded to that carbon in an alcohol. So that would be marked wrong. We would lose a mark for that. Likewise, an aromatic example, the correct way to draw nitrobenzene would be the nitrogen bonded to the carbon of the benzene ring. That, unfortunately, is the wrong way to do it. Next thing we'll look at are curly arrows. So these show the movement of an electron pair. And curly arrows must start from either center of a covalent bond, a lone pair, or the delocalized ring of pi electrons of a benzene ring. So I'll show you some examples now of those. So there's the first bullet point. So you can see the curly arrows starting from the center of that covalent bond, and likewise there as well. Second one, so the curly arrows starting from the lone pair on the O minus, and the third one starting from that delocalized ring of pi electrons in that benzene ring. Next thing we'll look at are units. So remember, moles are calculated using grams, and often the mass won't be in grams. So often they'll be in kilograms, milligrams, tons, etc. So here are the conversions. A kilogram is 1,000 grams, 10 to the 3 grams. A milligram is 10 to the minus 3 grams. And a ton is 1,000,000 grams. Moving on to significant figures. So very often in questions it'll say give your answer to an appropriate number of significant figures. So what you need to do is look at the data in the question and use the least accurate measurement in the data. It's often 3, but just check in the question. Another common thing is a question says give your answer to a certain number of significant figures, and all I can say here is double check, triple check. Read the full question. State symbols, if it asks for them, write them. Remember to read the full question. Make sure they're clear, and if the examiner's in any doubt what you've written for a state symbol, I'm afraid you won't get the mark. This is what I mean here. So I've written this. My handwriting's not great. Sometimes if I'm going quick, that there, is it an S? Is it a G? Whoever's marking this is not going to know. So it would be marked wrong. It needs to be clear. A couple of slides on percentage yield. So let's suppose X grams of chemical is reacted. The process has that yield, 72%. Calculate the mass of the product that's going to be made. So the first thing you do is calculate the moles of the reactant that's being used. You then use the mole ratio to calculate the moles of product, assuming 100% yield, and then we scale down by multiplying by the yield. So it will be multiplying by 0.72 in this case to scale down, because obviously we're not going to make as much as we should. And then the opposite of that is a question like this. A process has a 72% yield. Calculate the mass of reactant required to make a certain number of grams of product. So again, we calculate the moles, but this time of the product being made. We use the mole ratio to calculate the moles of reactant required, assuming it was 100% yield. And then we need to scale up now to factor in the drop from the yield. So we do that by dividing by the yield. So dividing by 0.72 in this case would scale up. Atom economy. So percentage atom economy can be calculated by either the MR of the desired product divided by the MR of all products times 100, or MR of desired product over the MR of all reactants times 100. Now the thing we've got to remember to do with atom economy is factor in any balancing numbers. So let's say you're trying to find out the atom economy for carbon dioxide. So if it's balanced in the equation with a 2, it would be 2 times 44. So 2 times the MR of CO2, not just 1. Addition reactions always have a 100% atom economy because there are no waste products. And a simple way to increase the atom economy of a reaction is to find a use for a waste product, and then it no longer is a waste product. So we'll move on to the individual topics now. So starting with the alkanes. So alkanes are unreactive due to the relatively high bond enthalpies of the bonds. So we've got CC single and CH bonds in an alkane. Also, the CC single and CH bonds are classed as non-polar. Obviously, CC bonds are non-polar, CH bonds classed as non-polar because the electronegativity difference is so low. You've got 4 sigma bonds around each carbon atom in an alkane, which gives it a tetrahedral arrangement, and the bond angle is 109.5 degrees. Sigma bonding involves end-to-end overlap between 2 orbitals, and because it's along the axis of the bonds can rotate freely. Alkanes undergo complete combustion if there's lots of oxygen, making carbon dioxide and water, but it's incomplete combustion if there's not enough oxygen, so you can get either carbon monoxide or carbon particulates and water. They react with halogens in the presence of UV radiation via the free radical mechanism. There's 3 steps to that: initiation, propagation, termination. And remember, initiation involves the homolytic fission of the halogen covalent bond, and homolytic fission is the breaking of a covalent bond where each atom receives 1 electron, and that produces free radicals. The mechanism is bad at making a single organic substance, and that's due to multiple termination steps. Substitution can continue, so further substitution, and substitution can be anywhere on the carbon chain. Moving on to alkenes. So alkenes contain at least 1 CC double bond, and that's made from a sigma bond and a pi bond. So you've got both types of bond between the 2 carbon atoms of a double bond. The pi bond involves the side-to-side overlap between 2 p orbitals, and it's a really, really good idea to draw a label diagram to give you something to talk about. Even if the question doesn't ask for one, I would still draw one. So what am I talking about here? Something like this. So these are just the carbons of the double bond. So you've got your 3 sigma bonds for each carbon, and then you've got these p orbitals. So there'll be an electron in each of these p orbitals. They overlap sideways above and below the sigma bond, and you get the pi bond. In terms of shape, we've got a trigonal planar arrangement around the carbons of the double bond, and the angle would be 120 degrees. Moving on to some reactions now. So in general terms, alkenes are more reactive than alkanes, and that's because the pi bond is weaker than the sigma bond. So reactions now: alkene with hydrogen makes an alkane, alkene with halogen makes a dihaloalkane, alkene with a hydrogen halide makes a haloalkane, alkene with steam makes an alcohol. All of these reactions are electrophilic addition, and an electrophile is an electron pair acceptor, And the electron pair that's accepted comes from the pi bond because it's on the outside of the alkene molecule. So still with alkenes, we're looking now at EZ and cis-trans isomers. So these are both types of stereoisomerism. So that's when you've got molecules with the same structural formula but different spatial arrangements. And that different spatial arrangement is brought about by the lack of rotation of the CC double bond, and it's the pi bond that prevents the rotation. To have these types of isomerism, each carbon of the CC double bond must have different atoms or groups attached. I'll illustrate all this in a second. And to make life easy for yourself, use a diagram and base it on an ethene molecule. Makes it much easier to show the relative positions of the groups across the double bond. So if you're given something like that structural formula there, that's not particularly friendly, turn it into something like these. So it's the same molecule, but we're basing it on an ethene structure. So you can see clearly how the different groups or atoms relate to each other across the double bond. So starting with EZ isomerism, that system compares the relative positions of the priority groups using the CIP rules, CIP rules. That stands for Carningel-Prelog. And that's based on atomic number. So the priority group has the higher atomic number of the two atoms bonded directly to the carbons of the double bond. So chlorine has a higher priority than carbon because it's got a higher atomic number. So the priority groups here are on the same side of the double bond. So this would be the Z isomer, whereas on the right hand example they're on diagonally opposite sides of the double bond. So that's the E isomer. And then thinking about cis-trans isomerism, so for a molecule to show cis-trans it has to be able to show EZ, but now we're comparing the relative positions of identical groups across the CC double bond. So you can see the identical groups are the chlorine atoms. So you can see they're on the same side. So this would be the cis isomer. That's the trans isomer. So still with the alkenes, major and minor products. So we're talking about addition to unsymmetrical alkenes, so something like propene. Addition of steam or hydrogen halide will give you two products. One's major, one's minor. The hydrogen adds first and produces a carbocation intermediate. So the major product forms from the most stable of the two possible carbocation intermediates. Tertiary, more stable than secondary, which is more stable than primary. And whatever you do, don't just talk about Markovnikov's rule. It's not enough. You've got to talk about the relative stabilities of those carbocation intermediates. And the final alkenes topic we'll look at is addition polymers, because these are obviously made from alkenes. So something like that structural formula is not particularly friendly. So base your monomer diagram on an ethene molecule. So something like that's much more friendly because it's really easy now to turn that into the repeat unit of the polymer. Literally, you just break one of the bonds in the double bond. So we've just got a single bond now between the two carbons. Obviously, that would be the sigma bond, and put two end bonds, but make sure they poke through the brackets. So we'll move on to the alcohols topic now. So alcohols contain the hydroxyl group, not the hydroxide group. Alcohols can form hydrogen bonds with water because obviously the lone pair on the O of the hydroxyl group can hydrogen bond with the H of a water molecule and vice versa. They can be primary, secondary or tertiary, so make sure you know what type of alcohol you're dealing with if you're answering a question on alcohols. Primary and secondary alcohols can be oxidized by heating with acidified dichromate 6 ions. Don't forget the acidified, and the colour change for that reaction is orange to green. The oxidation products from the primary alcohol's oxidation depends on the heating method used. So if you heat by distillation, basically you're taking the aldehyde product away from the oxidizing agent and you end up with just the aldehyde. If you do it under reflux, the aldehyde drops back into the heating flask and it gets oxidized to the carboxylic acid. When you're writing equations, remember that water is only made in the first oxidation when the aldehyde's made. If you oxidize a secondary alcohol, you can only make a ketone, so it's a lot simpler. And obviously tertiary alcohols can't be oxidized. When you heat an alcohol with a mixture of a sodium halide and sulfuric acid, it's going to make hydrogen halide, and then that reacts with the alcohol, and the OH group, the hydroxyl group, substitutes for whatever the halide is. When you heat an alkene with a strong acid catalyst, H2O, I always tell my students to think of it as HOH. So H2O is eliminated, and that makes an alkene. And the thing to remember is the hydrogen, the single hydrogen in the HOH, is removed from an adjacent carbon to the OH carbon. So where those two carbons are, the one with the OH on and the adjacent carbon, you're going to get a double bond forming there. And you get the alkene. And whenever you make an alkene in any reaction, you should always ask yourself, can it show EZ isomerism? Moving on to haloalkanes now. So carbon-halogen bonds are polar due to the significant differences in electronegativity values of the atoms. Halogens are always more electronegative than the carbon. Haloalkanes are hydrolyzed to make alcohols. So if you hydrolyze with an aqueous alkali, you get the alcohol and a halide ion. If you hydrolyze with H2O, you still get the alcohol, but you get a hydrogen halide in solution. So you get the H plus ion and the halide ion. The reaction is nucleophilic substitution, and a nucleophile is an electron pair donor. So there's a pair of electrons on the O of the hydroxide ion, so that's donated to the slightly positive carbon. Or if you're doing the H2O version, there's a lone pair on that oxygen and it's donated to the slightly positive carbon of the haloalkane. If you add silver nitrate solution to that mixture, you can get a measure of the rate of hydrolysis because the reaction will produce a silver halide precipitate. So you can see in both of these examples here, you get a halide ion produced. Well, the silver ions from the silver nitrate solution will create a silver halide precipitate. So you'd get a white precipitate if that was a chloride, cream if it was a bromide, and yellow if it was an iodide. And the relative rate of hydrolysis, remember, is all dictated by the strength of the carbon-halogen bond. So iodoalkanes are hydrolyzed the fastest, and that's because the CI bond is the weakest of the three carbon-halogen bonds. Chloroalkanes hydrolyze the slowest because the CCl bond is the strongest. Moving on to haloalkanes and the environment now. So chlorofluorocarbons, CFCs for short, they are haloalkanes, and these are broken down in the stratosphere by UV. And it's the CCl bond that breaks by homolytic fission, and that's going to generate a chlorine radical. CFCs aren't broken down lower down in the atmosphere because the bond enthalpies are relatively strong. And it's these chlorine radicals that are produced that are responsible for the breakdown of ozone. We need ozone in the stratosphere because it protects us and plants from harmful UV from the sun, and that harmful UV damages DNA. So we'll just run through the mechanism now. So initiation first, there's your CFC, chlorofluorocarbon. So UV breaks the carbon-chlorine bond by homolytic fission, produces that very reactive chlorine radical. So that chlorine radical that's just been produced attacks an ozone molecule in the first propagation step. That generates that CLO radical and an oxygen molecule. And then that CLO radical attacks an oxygen atom that's also up there in the stratosphere, and it reforms the chlorine radical when it makes another oxygen molecule. So you can see when we're going to add these two equations together to get the overall equation. You can see the chlorine radicals cancel each other out, and so do the CLO radicals as well. So overall, that's the reaction, which is bad news for us because it shows that ozone is being broken down irreversibly. And because the chlorine radical is reformed in the second propagation step, it's a catalyst. So we'll move into aromatic chemistry now. So I've got a few slides all about benzene, and then we'll move on to phenol. So we'll start with the Kekulé structure for benzene. So that's obviously this one here with the alternating carbon-carbon single and double bonds in that hexagonal ring. So it's always good to draw a diagram if you're trying to explain something. I know this looks a bit complicated at the moment, but it's really easy to draw. So we'll just talk through what's happening there. So each carbon atom is using 3 out of its 4 outer electrons to form 3 sigma bonds. So if we just pick that carbon there, so it's forming a sigma bond with that carbon, it's forming a sigma bond with that carbon, and it's forming a sigma bond with that hydrogen. So the 4th electron is in a p orbital, so I've represented that with the upper pink lobe and the lower blue lobe. So to get Kekulé's structure, what's got to happen is you've got to have alternating lobes of p orbitals overlapping with each other. And what that would generate would be 3 specific alternating carbon-carbon double bonds. So you've got carbon-carbon double there, then you've got carbon-carbon single, just the sigma bond there, back to double, single, and so on. So that was Kekulé's proposed structure. And we'll go on to the evidence that disprove this in a moment, but we'll just talk about the delocalized model now. So that's this representation for benzene. So exactly the same thing to start with, so I won't bore you with that again. But what they found happened was all of the p orbital lobes overlapped with each other. And so the upper lobes overlap, the lower lobes all overlap, and what that generates is that. So that's called the delocalized ring of pi electrons. It's formed above and below the plane of the ring, and that's going to be occupied by those 6 electrons. Remember, each carbon atom has a spare electron in a p orbital, but they're able to exist in this pi system here. So if we move on to the evidence that cast doubt on Kekulé's model, remember this is Kekulé's, this is the delocalized model. So the first bit of evidence is the carbon-carbon bond lengths. They were found to be all the same, and they are intermediate between the slightly longer carbon-carbon single to the slightly shorter carbon-carbon double bonds. Second bit of evidence is all about the enthalpy change of hydrogenation. Just be careful you don't say hydration, it's hydrogenation. So that was found to be less exothermic than expected. You don't need to remember the numbers, but they are minus 208 was the actual, but they expected it to be minus 360 kilojoules per mole because they were comparing it with cyclohexene, which they had measured at minus 120 kilojoules per mole. So 3 carbon-carbon double bonds should be 3 times that, but it wasn't. It was less exothermic than expected. The final bit of evidence was about how benzene actually reacted. So they found that it was resistant to reaction. It needs a catalyst when it reacts, and it undergoes substitution reactions and not addition reactions. So we've just said it reacts by substitution, not addition. Well, it's actually electrophilic substitution. So we'll just have a quick look at the typical mechanism for that. So in the mechanism, a pair of electrons moves from the delocalized ring of pi electrons to the electrophile, not from the hexagon. So your curly arrow must start from the circle and go to the electrophile. The intermediate that's formed from that has a partial pi electron cloud, and I always tell my students to cover 5 of the carbon atoms in the ring, and you leave it open where the substitution's taken place. So it looks like that, and we now show the hydrogen that's already attached to the ring, but we show it because we need it for the next part of the mechanism. And the third thing to happen is the H is lost as an H plus ion. A pair of electrons from the CH bond go back into the ring and reform the full delocalized ring of pi electrons, and the H comes off as an H plus ion, so don't forget the H plus. So we'll move on to the reactivity of benzene compared to alkenes. So benzene is less reactive than alkenes. Remember, it's substitution, not addition. It needs a catalyst when it reacts. So what's that down to? It's due to the nature of the pi electrons. So remember, in benzene, the pi electrons are delocalized, and that means that the pi electron density is lower compared to alkenes because it's spread over all 6 carbons in the ring. So benzene is unable to polarize electrophiles. It can't attract them as strongly as an alkene can. And then we'll just do the like-for-like comparison. So in the carbon-carbon double bond of alkenes, the pi electrons are localized, shared between 2 carbon atoms. The pi electron density therefore is higher compared to benzene, and so alkenes can polarize electrophiles. They can attract them more strongly. We'll move on to phenol now. I've got a couple of slides for this. So remember, phenols are aromatic compounds that have a hydroxyl group directly bonded to the benzene ring. They're more reactive than benzene. They react with an excess of bromine without a catalyst, and they make 2,4,6-tribromophenol. The bromine is decolorized in that reaction, and it also produces a white precipitate. Phenols will react with dilute nitric acid without a catalyst and at RTP, whereas benzene needs concentrated nitric acid, it needs a concentrated sulfuric acid catalyst, and it needs a temperature of around 50 to 55 degrees C. Phenols are weak acids, but they can react with strong bases, so for example sodium hydroxide, and that would make a phenoxide salt. So the example there is the product from the reaction of phenol with sodium hydroxide. That's called sodium phenoxide. However, they're too weak an acid to react with a weak base such as sodium carbonate, so you wouldn't get the expected bubbles of CO2 produced in that reaction. The final phenol slide's about the reactivity compared to benzene, so a very similar slide to the one you saw with the alkenes. So phenol is more reactive than benzene. That's down to the nature of the pi electrons. Remember, in benzene the pi electrons are delocalized. The pi electron density in benzene is lower compared to phenol. Benzene can't polarize electrophiles, can't attract them as strongly. In phenols, you've got a lone pair of electrons on the oxygen of the hydroxyl group, so that becomes delocalized into the ring. That's going to increase the pi electron density, and so phenol can polarize electrophiles. It can attract them more strongly. And the final aromatic slide is about directing groups. So in an unsubstituted benzene ring, in other words benzene, all the carbon atoms are the same, so the electrophiles can react with any one of them. As soon as you put a substituent group on a benzene ring, that changes the electron density of certain atoms, and the ones you need to know about are the OH group and the NH2 group. So they are electron donating groups. They have electrons in orbitals that overlap with the delocalized ring of pi electrons and increase its electron density at carbons 2, 4 and 6. So moving on to the opposite scenario to that now. So the NO2 group is the only group that you need to know about off by heart. That's electron withdrawing. So it doesn't have any electrons in orbitals that can overlap with the delocalized ring. It's an electronegative group, so it withdraws electron density from the ring, but specifically from carbons 2, 4 and 6. So what that does is it leaves kind of the highest electron density on positions 3 and 5, and that's where it directs substitutions to. Now obviously there are other directing groups, but if you've got a question about any of those, you will be told about their effects. Next topic we'll look at is the carbonyls topic. So aldehydes and ketones contain the carbonyl group, that's a C double bond O. In an aldehyde, the carbonyl group's at the end of the carbon chain. So on that end carbon, you've got the C double bond O and also a hydrogen attached to the carbon. Whereas in a ketone, the carbonyl group's within the carbon chain. So either side of a carbon, you've got the C double bond O attached. Aldehydes are oxidized by acidified dichromate 6 ions. There's the formula in the bracket there you can use, and they give carboxylic acids. And the colour change associated with that reaction is orange to green. The oxidizing agent is orange in colour and it goes green in the reaction. Ketones are not oxidized, so because of that the acidified dichromate 6 ions will stay orange. Aldehydes and ketones are both reduced by the reducing agent NaBH4, and they both make alcohols. Aldehydes make primary alcohols, ketones make secondary alcohols. In the reaction, 2 moles of reducing agent are needed per carbonyl group reduced, and we use that H in square bracket symbol for the reducing agent. We don't put NaBH4 into the equation. Aldehydes and ketones both react with hydrogen cyanide, but remember that's made from a mixture of either potassium cyanide or sodium cyanide in acid, and they both make hydroxynitriles. So we'll just move on to testing for the carbonyl group. I do have a slide later on that covers all of the organic tests, but specifically carbonyls, 2,4-DNP, 2,4-dinitrophenylhydrazine, is used to detect the presence of the carbonyl group, and the positive response for that is an orange precipitate. Tollens reagent, so that's a mixture of silver nitrate and ammonia. That's used to distinguish between aldehydes and ketones. It's also used to test for an aldehyde, but I'll come on to that later. So aldehydes will give a silver mirror, ketones don't. If you wanted to identify the specific carbonyl compound, you can do that by measuring the melting point of the purified 2,4-DNP derivative. So that orange precipitate gets purified by recrystallization. You measure the melting point and you compare that to known data values. And that's often referred to in questions of an example of a non-spectroscopic technique. Moving on to carboxylic acids, very quick slide this one. So short chain carboxylic acids are highly soluble in water due to their ability to hydrogen bond with the water molecules. So often you would draw a diagram to go along with that statement, and I just wanted to point out a few things that they're going to be looking for. The dipoles must be shown on the polar bonds, and you show the lone pairs on the oxygen, and the hydrogen bond must go from a lone pair on the oxygen to a hydrogen on a neighbouring molecule. Carboxylic acids react with metals, so they give a carboxylate salt and hydrogen. They react with metal oxides and metal hydroxides to give carboxylate salts and water, and they also react with carbonates to make carboxylate salts, water and carbon dioxide. There's the general formula for a carboxylate salt, and just be careful when you've got a carboxylate salt of a group 2 metal, because you need 2 moles of the carboxylate ion for 1 of the metal 2 plus ion. Next topic we'll look at is acyl or acid chlorides. So they've got the functional group COCl, so that's a C double bond O with a chlorine also bonded to the carbon. They're made by reacting carboxylic acids with a chemical called thionyl chloride, which has the formula SOCl2. The OH of the carboxylic acid is replaced by a Cl, so that's where that functional group comes from. Acyl chlorides are very reactive. In all the reactions, the chlorine combines with a hydrogen of the reactant molecule, so you always make HCl when acyl chlorides react. So what do they react with? They react with water to form carboxylic acid and HCl. They react with alcohols to form an ester and HCl. They react with ammonia to form a primary amide and HCl. They react with primary amines to make a secondary amide and HCl, and they react with secondary amines to make a tertiary amide and HCl. They also react with phenol, and that's going to make a phenyl ester and HCl, and that's what a phenyl ester looks like. So this part here has come from the phenol, this part here has come from the acyl chloride. Moving on to esters, so they contain the COO group. So the C double bond O also has a single bonded O on the carbon. Esters can be made in a few ways, so they can be made from carboxylic acids and alcohols, and that makes ester and water, but that reaction needs a concentrated sulfuric acid catalyst and some heat. They can also be made by an acyl chloride, we've just seen that reaction, so acyl chloride and alcohol will make an ester plus HCl gas. If you want to make a phenyl ester, that's acyl chloride and phenol. And you can also make an ester using an acid anhydride with an alcohol. So as well as the ester, you make a carboxylic acid. We also need to remember that esters can be hydrolyzed. So they can be hydrolyzed by hot aqueous acid. That's going to generate a carboxylic acid and alcohol. So effectively, it's the reverse of this esterification reaction here. They can also be hydrolyzed by hot aqueous alkali. And in that reaction, you generate a carboxylate salt, but also the alcohol. We'll look at some nitrogen compounds now. So starting with amines. Amines can be primary, secondary, or tertiary. Amines act as bases, so they accept H plus ions by using the lone pair on the nitrogen, and that's going to form a coordinate bond. The nitrogen's providing both electrons in the covalent bond with the H plus ion. and that generates ammonium salts. Primary aliphatic amines can be made by reacting haloalkanes with an excess of ammonia, but the ammonia needs to be dissolved in ethanol, and the excess ammonia avoids further substitution to secondary and tertiary amines. If you want to make an aromatic amine, that's done by reducing a nitroarene with a mixture of tin and concentrated hydrochloric acid. Don't mix up the reducing agent. Remember, you've seen NaBH4 used to reduce carbonyl compounds to alcohols. We use a different reducing agent to reduce a nitroarene, so just watch out for that one. In the reaction, you need 6 moles of reducing agent per NO2 group reduced. You can also make amines by reducing nitriles. I've got a slide about nitriles coming up, and we use hydrogen and a nickel catalyst for that one. So the CN, the nitrile group, becomes CH2NH2. So you can see you've got 4 more hydrogens there, so you need 2 moles of hydrogen in the equation. We'll have a quick look at amides now. So amides can be primary, secondary or tertiary. So that's what they look like. Most common mistake I see is students mixing up the amide group for the amine group. So just be careful with that. So an amide has a nitrogen directly bonded to a C double bond O, whereas an amine just has the nitrogen directly bonded to the carbon group. And the other thing we need to know about amides is, just like the ester group, the amide group can also be hydrolyzed by hot aqueous acid and hot aqueous alkali, and it's this CN bond that breaks. Moving on to amino acids now, more specifically alpha amino acids. They're the ones we look at. They have the NH2 and COH groups bonded to the same carbon atom. So that means they have that general formula. They all show optical isomerism except glycine. That's where the R group is just a hydrogen. I've got a more detailed slide on optical isomerism coming up, so I won't say any more about that. In terms of reactions, the carboxyl group can react with alkalis, so that'll generate a carboxylate salt. The carboxyl group can also react with alcohols in the presence of concentrated sulfuric acid, so that's going to generate an ester group. And the NH2 group can react with acids. Remember, the nitrogen's got a lone pair on it, can accept H plus ions from acids and generate ammonium salts. And the sort of top tip really there is beware of the carboxyl groups and NH2 groups in the R group, because they will also react with those things as well. As promised, a slide on optical isomerism now. So it's a form of stereoisomerism, so that means they've got the same structural formula but different spatial arrangements of the atoms or groups. Optical isomers are described as being non-superimposable mirror images of each other. They're also known as enantiomers, and it's possible if the molecule has what's called a chiral center. So that's where you've got a carbon atom in the molecule with 4 different atoms or groups attached. For each chiral center in a molecule, there's a pair of optical isomers possible. So the total number of isomers possible is 2 raised to the power of the number of chiral centers. So we'll have a quick look now at how you draw optical isomers. So the first thing you do is identify the chiral center. I'll show you all this in a second. You then draw what I call an empty tetrahedral structure. You add your atoms or groups, and then you do the mirror image of what you've drawn. So there's a structural formula. So we identify the chiral center. It's that carbon there. So we just draw an empty tetrahedron, and now what I need to do is start adding groups. And it doesn't matter which way around you do them, so long as your mirror image is a reflection of what you've drawn. So the right hand molecule must be the mirror image of the left hand one. You could be asked about a 2 chiral center molecule, so there would be 4 possible optical isomers, the one on the screen now. So how do you go about doing the others? So the sort of logical approach I would take is mirror both of your chiral centers. So you can see that chiral center is the mirror of that one's the mirror of that one. Then you could just mirror the top, and then you could just mirror the bottom. So we'll move on to nitriles now. So nitriles contain the CN functional group, so there's a triple bond between the carbon and the nitrogen, they're formed by reacting haloalkanes with ethanolic cyanide ions. So all that means is the source of cyanide ions is dissolved in ethanol. It's just a solvent that helps the chemicals mix together better. You can also make the nitrile group by reacting a carbonyl compound, so an aldehyde or a ketone, with hydrogen cyanide. But that's going to make the hydroxynitrile. So what can you do with nitriles? Well, you can turn nitriles into amines by reducing them, and that's by reacting with hydrogen and a nickel catalyst. You can also hydrolyze them into carboxylic acids, and that's done by reacting them with an aqueous acid. So, for example, a mixture of HCl and water. So we'll move on to condensation polymers now. So we'll start with polyesters. So polyesters can be made from either 1 or 2 monomers. So I'm going to look at a 2 monomer example. So we've got a dicarboxylic acid here. Obviously the little n just means there's lots of them. And we've got a diol. So to make the ester group, we need to remove an H and an OH and join the monomers together. So the way I'm going to do it is I'm going to take the OH from the carboxylic acid and the H from the alcohol. Now you can do it the other way around if you want, but I'm going to do it this way. So what that's going to do is obviously it's going to form a water molecule, but it's going to join those 2 monomers together, and you can see there's that ester linkage there. And that's obviously possible from a single monomer so long as you've got both functional groups present. So you need the carboxyl group and the hydroxyl group in that same monomer if you're going to do it from 1. Now you can also make polyesters from diacyl chloride. So imagine this molecule here, instead of being COOH, it's COCl. So if you could do it that way, but instead of making water, you would make HCl instead. Moving on to the other type of condensation polymer, so that's a polyamide. So this is a 1 monomer example. So to make an amide group, you could have an amine group at one end and a carboxyl group at the other end. Same logic as before, we're just going to remove an H and an OH group, and we're going to join them together. But this time, obviously, you're sort of limited to an H from the amine group and the OH group from the carboxylic acid group. So what would that look like? It would look like that. So there's the amide linkage there. Obviously that's split across the repeat unit, but remember what's going to be at the end of that bond there, it's going to be the beginnings of the next repeat unit. So you'd have the nitrogen with the hydrogen on, so your amide linkage would also be there as well. And obviously that's possible from 2 monomers with the required functional groups at each end. So the next thing we'll look at is the hydrolysis reactions of these esters. So there's acid hydrolysis and alkaline hydrolysis. So starting with acid hydrolysis, so what's going to happen is the bond, the linkage in the polyester or the polyamide, that one there, sorry, is going to be broken. So the way I think about it is I split the polyester or the polyamide and attach the H and the OH from the water molecules. That's the first thing I kind of do in my head. And then the next thing I do is look at, in this case, where the H plus ions from an acid could also attach. So any nitrogens present will accept protons, remember, because they've got the lone pair on the nitrogen, and accept an H plus by forming a coordinate bond. So if we look at what the product of these would be, so there's nothing on these that could accept H plus ions, so you're going to get the dicarboxylic acid back and the diol. Whereas on this one, this would have started as an NH2 group, but remember the nitrogen can accept H plus, so it becomes an NH3 plus group. Obviously that would just stay as a carboxylic acid group. And then if we move on to the alkaline hydrolysis, I'm deliberately using the same polymers so you can compare with the previous example. First thing's exactly the same, split the polyester polyamide, attach the H and OH from the water molecule, and then secondly, look at where H plus could be lost from the products. Remember, it's alkaline hydrolysis, there's OH minus ions present that can accept H pluses. So in this case, it will be an H plus ion from a carboxyl group, and that's going to become, therefore, a COO minus group. So let's see what happens here. So you can see the dicarboxylic acid that would originally form then becomes the dicarboxylate salt there. And then on this one, you can see that that carboxyl group has now become the O- there. Obviously, if it specified the alkali, if it said it was NaOH, you would have Na plus alongside there, and likewise there. And then the final slide I've got for polymers is their environmental impact. So remember, addition polymers are non-biodegradable, whereas as we've just seen, condensation polymers, polyesters, polyamides, they can be hydrolyzed, so they can be broken down. Many polymers are thrown away, unfortunately, so they can end up in landfill, they can end up in the oceans and obviously pollute them, broken down into microplastics, absolutely terrible. And many polymers are derived from crude oil. Remember, that's a finite resource. So we'll just look at some solutions to the problem. So scientists are developing new polymers from renewable sources, starch and corn, for example. They're developing photodegradable polymers. So these polymers contain bonds, so seedable bond is the classic example, which can absorb sunlight, vibrate more, and obviously helps break down the polymer. Polymers can be converted back into the original monomer and used as a chemical feedstock. And polymers can also be combusted, burned for energy production, but obviously beware of polymers containing chlorine. These are particularly nasty because they can form corrosive, toxic hydrogen chloride gas. So you'll be placing over in the last lap now. We've just got some practical slides and then I'll finish with the spectroscopy stuff. So first practical thing we'll look at is the synthesis of an organic liquid. So once you've synthesized your organic liquid, the mixture that you've got left in the flask will often contain an organic liquid, the one that you're trying to make, and some aqueous substances. So how do you end up with just the pure organic liquid? So the first thing you'd do is pour the mixture into a separating funnel, which looks like that. If you've used any acid as part of your synthesis, you need to neutralize it. So you can do that in the separating funnel by adding sodium carbonate solution. Obviously, you're going to see bubbles of CO2, and when the bubbles have all gone, that means all of the acid's been neutralized. You then allow the two layers to settle and then use the density information, if it's supplied in the question, to establish the layers. And just remember that the density of water of aqueous substances would be 1 gram per cubic centimetre. So if the organic substance that you're making has got a density higher than 1, then it's going to be the lower layer. If it's less than 1, it's going to be the upper layer. The organic layer is not always upper or lower. It all depends on the relative density compared to water. If the density information isn't given, there's a little trick you can do. You can add water to establish the aqueous layer, because obviously the water is going to make the aqueous layer get bigger. So once you've established which one is the organic layer, you collect that. Don't forget to say which layer it is. And there's going to be a tiny amount of water left in that layer, so you would dry it by adding a drying agent. The one I always quote is anhydrous calcium chloride. Obviously there are others. Anhydrous magnesium sulfate's another one that I seem to remember okay. Just make sure you have one remembered that you can give as an example. So let's just suppose the organic liquid that we are making has a boiling point of 64 degrees C. How would you make sure that you just end up with that? Well, you would distill your dried product. Remember, dried just means that all the water's gone. You distill that and collect the fraction that boils at 64 degrees C. So we'll just have a quick look at how do you determine the purity of the liquid that you've made. So there's various things you can do. You can measure its boiling point. It should match known data values. It should boil over a narrow range. Impurities, if they're there still, would elevate the boiling point. It would make it higher, and it would make it boil over a wider range. You could do some TLC, thin layer chromatography, measure the RF value, and compare to known data values, or you could run the TLC of your substance and compare it to a chromatogram of a pure sample. You could also run your sample and the pure sample on the same TLC slide and compare them directly. The final thing you could do is run some spectroscopy, so you could do NMR, IR, mass spec, and again compare your spectrum of your sample to the database and see how closely they match. On to the synthesis of an organic solid. So you would purify your organic solid by recrystallization. So how do you do that? You dissolve your solid in the minimum volume of hot solvent. You would then cool it back down again to recrystallize, and the impurities that are present would stay in solution. You would filter using Buchner apparatus, or you could call it reduced pressure filtration, which looks like that. And a couple of years ago they actually asked people to draw that, so make sure you know how to draw it in case it's asked again. You would wash with cold solvent now, because obviously if you use hot solvent your sample is going to dissolve and you don't want that. So wash with cold solvent and then you allow it to dry. How do you determine purity? Well, very similar to before, but this time we measure the melting point and we compare to known data values. It should match the data closely. It should melt sharply, i.e. over a narrow range. Or you could do exactly the same as we said on the previous slide, those three things there. Next couple of slides is just looking at how you draw the quick fit apparatus. So we'll start with distillation, some key things to point out here. So obviously you've got a flask with some chemicals in, you need a heat source, thermometer, make sure your bulb of your thermometer is in line with the central part, the central tube of the condenser. Obviously this is your condenser here. Make sure you get the water flow direction right, so water always goes in at the bottom of a condenser and it comes out at the top. If you get it the wrong way around, the condenser doesn't fill up efficiently, so you get like air bubbles in it. So it goes in at the bottom, out at the top. And then a beaker, a container to collect your distillate, so that's what comes off distillation. And make sure that's not sealed up, okay, so it needs to be left open. Moving on to reflux apparatus, so some key things here. Obviously a flask, come do a pear-shaped flask if you want. Heat source, just make sure there's no gaps here so that the vapours as they form go up the central part of the condenser. You've got the water in at the bottom, out at the top, and a key thing on this one is make sure you leave the top of your condenser open. That should never ever be blocked off. Next slide's just going to run through the tests for the various organic functional groups. So here we go. So alkenes reacting with bromine. The bromine is decolorized. I hope you can appreciate what I've done there. Took me about 3 minutes to do that. You're welcome. Carboxylic acids, you add sodium carbonate and you get bubbles forming, which is CO2. Primary and secondary alcohols, you can heat them with acidified dichromate 6 ions and you get the orange to green colour change. Remember, aldehydes can also be oxidized, so they will give that same response there. Haloalkanes, you can react them with aqueous silver nitrate in ethanol, and the observations for these. Chloroalkanes will give you a white precipitate of silver chloride. Bromoalkanes, a cream one, and an iodoalkane will give a yellow precipitate of silver iodide. Moving on to phenols, there's several ways to test for a phenol. The one I always go for is this one. You test the acidity by pH measurement. Remember, phenols are very, very weak acids, so they should be indicated as acids by that. Then you could add sodium carbonate and you don't get any bubbles. So remember, carboxylic acids are really the only other acidic substance we look at A level. So they're acidic, they will give bubbles of CO2, whereas a phenol is acidic, but it won't give bubbles of CO2 with sodium carbonate. Another thing you can do is react a phenol with bromine, and the bromine is decolorized and you get a white precipitate. Another thing you could do is you could react it with FeCl3, iron 3 chloride, or ferric chloride it's also called, and you get a violet purple solution. Moving on to carbonyl compounds, you would add 2,4-DNP and you would get an orange precipitate. So if you did that test, you would then know that you've either got an aldehyde or a ketone present. So how could you differentiate between those two? Well, aldehydes you could heat with Tollens reagent, so that's ammonia and silver nitrate solutions, and you get a silver mirror. To determine if you've got a ketone, you would add 2,4-DNP to get that orange precipitate to confirm it's a carbonyl, and then you'd add Tollens and you wouldn't get a silver mirror. Moving on to chromatography, so starting with thin layer chromatography, TLC. So the separation is achieved by relative adsorption. Just be careful there, you don't say absorption. So the different components in your mixture will bind to the solid stationary phase by differing amounts. So if it's strongly adsorbed, it's not moved as far up the plate as one that's weakly adsorbed. That gives you an RF value, which you can measure by taking the distance travelled by the spot and dividing by the distance travelled by the solvent, which is obviously your mobile phase. How do you know what you've got? You compare the RF value of your substance with known data values, or you could run a chromatogram alongside that of a known substance and compare them. Moving on to gas chromatography, or GC for short. So separation there is by relative adsorption if the stationary phase is a solid, so that works exactly the same way as TLC. But if you've got a liquid stationary phase, which you can have in gas chromatography, it's by relative solubility. GC measures retention time, so that's the time it takes from injection to detection. How do you know what you've got? You compare the retention time of your sample with known data values. So on a gas chromatogram, the different components in the mixture give peaks with different retention times, and they have a measurable area. Don't worry, you don't have to measure the area, you would be given that. And the area under the peak is proportional to the relative amounts of the components in the sample. And the relative proportions are measured by dividing the area under a particular peak by the total area under all of the peaks. If you wanted to know the actual concentration of a substance in a mixture, you would use a calibration curve. So the way you do that is you measure the area under a peak for known concentrations of that substance. You would then use that data to plot a calibration curve. Then to find the concentration of the sample in your mixture, you would compare the area under its peak with the area on the calibration curve, and obviously that correlates to a particular concentration. So moving into the last few slides now, so mass spectrometry next. Mass spectrometers measure the mass to charge ratio, or M/Z for short. The charge of the ions that causes the peak is 1+. Whatever you do, don't forget the positive charge on your formulae. It's a really common mistake and it's so easy to put right. The significant peak that's furthest to the right on your spectrum is called the molecular ion peak, or M+ peak for short. That tells you the MR of the full molecule. Sometimes you see a tiny little peak that's 1 unit higher than the molecular ion peak. That's called the M+1 peak. Basically, that's due to one of the atoms being replaced with an isotope that's one heavier. So the classic example there is carbon-13. Remember, you don't just get this molecular ion peak, you get fragment peaks. So the easiest way to think about fragment peaks at A level is just start with your molecular ion and break one covalent bond in it. So some examples there. If you've got a peak at M/Z15, it's due to a methyl fragment, CH3+, don't forget the plus charge. Peak at 29 would be due to an ethyl fragment, etc. And remember, fragmentation patterns are unique to molecules. It's like a molecular fingerprint for the molecule. So we'll move on to infrared spectroscopy now. Remember, you're not expected to identify every single absorption. And any absorptions you do identify, annotate your spectra. You will get credit for correct annotations. So all I'm going to do is have a look at some typical spectra now. So this one here, there's only 2 key absorptions that I would bother to annotate. So there's this one here. So you'd obviously go to your data sheet. You've got that starting at about, 2225, and it's going all the way to 33. So you look on your data sheet, which bond is causing that absorption. It's the OH bond of an acid. I would always say what type of OH it is. So we've got an OH of an acid there. We've also got a C double bond O there. So what can you deduce from that? You've got a carboxylic acid. Remember, this area here, that below 1500 cm to the -1, is called the fingerprint region. It's very, very difficult to interpret, and it's unique to a particular molecule. Moving on to this one here, so there's only really one absorption I would bother to annotate, and that's that one there. So this is the OH of an alcohol this time. These absorptions here are due to CHs. Now, unfortunately, you don't get a mark for identifying the CH because virtually all organic compounds have CH bonds. So what can we say about this molecule? It's going to be an alcohol. Moving on to this one here, this is the last infrared spectrum we'll look at. So what would I say about this? Well, I would probably say that we haven't got an OH of an alcohol or a carboxylic acid. So no OH there. Remember, these are your CHs. We're not going to get any marks for that. This is key though. This is a C double bond O. So what could we say now about this molecule? Well, it could be an aldehyde, it could be a ketone, it could be an ester. So we're into the final topic now, hooray! And it's my personal favourite, NMR spectroscopy. So we'll start with some basic stuff first. So carbon-13 and hydrogen-1 nuclei have an odd number of nucleons. So that's protons and neutrons added together, which means they have a property called spin. So they can act like little tiny bar magnets. Because of this property, they can absorb energy in the radio wave part of the electromagnetic spectrum. So the energy that's used in NMR is radio wave energy. The different chemical environments for a nuclei will absorb different amounts of this energy, and that gives you your different chemical shift values. So there's some key molecules used in NMR. So the first one we'll talk about is the reference molecule. That's TMS. Tetramethylsilane, there's its formula, so that sometimes crops up as a 1 marker, and that's assigned a chemical shift value of 0 ppm, 0 parts per million. So that's your reference molecule. Another key substance in NMR is the solvent molecule, so we use deuterated solvents in NMR. So there's an example there, that's the one I always remember, and I tell my students remember, CdCl3. So basically the regular hydrogen-1 atom has been replaced with a deuterium atom. So deuterium has 2 nucleons, has a mass number of 2, so that's an even number, so it doesn't have any spin. So you're not going to get a signal from hydrogen 1 because it doesn't have 1, it has deuterium. Another important molecule is D2O. Now, students often get the 2 deuterium substances mixed up. So D2O is used in proton NMR, H1 NMR, to remove OH signals and NH signals. Basically, the hydrogen ones swap for the deuterium and the signals disappear. Okay, so we'll take a closer look at carbon-13 NMR now. So what does carbon-13 tell us? It tells us 2 things about a molecule. It tells us the number of different chemical environments for the carbons in the molecule, and that's from the number of peaks. And it also tells us what type of chemical environment they're in, so what they're bonded to basically, and that's from the chemical shift value, which is on the data sheet. And another thing to be aware of is to look for symmetry. So it's a quick way to spot equivalent carbon environments that you've got in a molecule. So I'll just show you a quick example of that. So we've got pentan 3-one and pentan 2-one. So we've got a line of symmetry running down here, down carbon 3. So any carbons that are sort of equidistant from the line of symmetry will be in equivalent environments. So the 2 end ones are equivalent, those are equivalent, and obviously that's unique. That carbon there is directly bonded with a double bond to the O. That's that signal there. Moving on to pentan 2-one, there's no line of symmetry anymore, so each carbon is in a unique environment. So that's why we see 5 separate signals. So we've got the 1 there for the C double bond O, and then we've got these ones here, these 4 here for those 4 regular carbons. So we'll just finish carbon-13 with an aromatic example. So we've got a line of symmetry running down here. So that means anything either side of that line are equivalent. So obviously that's unique there. So that's one environment. That's unique there. But then we've got equivalents on the blues, equivalent on the greens, and unique for the orange. So moving on to hydrogen-1 or proton NMR now. So this tells us 4 things about the molecule. It's a much more powerful spectroscopic technique. It can tell us the same 2 things as carbon-13, but it can also tell us the relative numbers of hydrogens in each type of environment, and that's from the relative peak areas, also known as integration values. It can also tell us the number of non-equivalent hydrogens that are adjacent to the hydrogen causing the signal. And that's from the splitting pattern using the n+1 rule. So for example, if you see a peak appearing as a triplet, so there's 3 lines in that signal, that means there's an adjacent CH2 group. A couple of other things to be aware of. OH and NH signals will always be singlets, and OH and NH protons do not cause splitting either. And just a reminder, OH and NH signals can be removed by adding D2O. So we'll have a look at a couple of examples now. So if you've watched my walkthrough videos, you'll know exactly what I'm going to do next. So we take each signal in turn and we say 3 things. And like we said on infrared, always annotate your spectra. So I'm going to use that signal there to illustrate this. So we'd say the signal at 2.3 ppm is a quartet. So the n+1 rule means that there's a CH3 adjacent to the protons that have caused this signal. You'll notice there's a little 2 above the signal there. That's the peak area, or the relative peak area, or the integration value. That means that there are 2 protons in this environment. And the shift value, obviously we get this from the data sheet, is telling us that the protons that have caused that signal are bonded to a carbon that is then bonded to a C double bond O. So it's in the H to C to C double bond O environment. And then what I always encourage my students to do, they don't particularly like doing it, but I would always try and do this if you can, draw that little part of the molecule out so you can start building up a picture of your molecule. So you can see I've highlighted this CH2 group. Remember the area was 2, so there's 2 protons in the environment. It's bonded directly to a C double bond O, and adjacent is a CH3 group. So if you can do that for all the other signals, you basically have got your molecule and you just have to piece it all together. Last slide, aromatic protons, very quick. So these always occur between 6 and 8 ppm. They are typically multiplets, not always, but typically are multiplets, so they'll be split. The area is typically greater than 1. I've never seen a pentasubstituted benzene ring tested at A level, so the area will typically be greater than 1. Remember, the peak area integration value tells you how many protons are in the environment, so in other words, how many protons are bonded to the benzene ring, and you're not expected to analyze the splitting patterns of aromatic protons. So don't worry about trying to explain the splitting pattern. So let's have a quick look at this spectrum here. So where are the aromatic protons? Obviously this signal here, because they're in that range. So you'll notice it is a multiplet. The area is greater than 1. So all we need to say about this is we've got a C6H4 group. In other words, we've got a di-substituted benzene ring. Well, I think that's the longest video I've ever made. Huge congratulations if you're still watching, poor thing. All I've got left to say is the very, very best of luck for your paper 2 exam. I'm sure you're going to smash it!